Okay, welcome back. We are moving on to section 12.2. This is global approximation and the Euler method. Global approximation because if I scroll up a little bit, you'll recall from our previous linearization example that, if we linearize and solve a Cauchy problem at an initial condition, we're going to gain a nice approximation, but it's only going to last for so long, right? I guess in this case, it was like y2 decided kind of to spread away from the true solution somewhere around 0.2, right? So somewhere around t equals 0.2, the two solutions no longer wanted to coincide very well. So this section is kind of like, how do we fix? I'll mention that here. How do we fix this spreading of the approximate solution to the real solution? Right, and there it's like at t's 0.7 or something, but over here it starts to split at maybe 0.25, I suppose, somewhere around 0.25. And the way we do this, and we're going to get into this below a little bit, is basically if I draw a line right here, both solutions coincide very well, and I've moved forward in time. Maybe I'll mention that here. So both solutions coincide and time has moved forward. So what about repeating linearization from this point? Repeat linearization from here. So we can basically run a linearization over a tiny time step, I guess 0.21 or something in this case. Then I find new points where I exist at, re-linearize, and then I would run a linearization over maybe another time step, and that linearization might get me here and here, and then I could re-linearize at these points, and then run it, and it probably gives me a much better approximation, because at each step it's calculating new tangent lines to the true curves, right? This is basically like saying I'm going to run along tangent lines to the curves, to the solution curves. How long will the tangent lines to the solution curves actually last? And if I only run along a tangent line over a very short period of time and then repeat, I'm going to get something that approximates very well. So I'm going to define just a few definitions to kind of get us this idea of global approximation. This first one is just going to be script A sub n. I'm going to call that a local nth order approximation map. Okay, so it inputs an entire Cauchy problem and it outputs an approximation at the initial condition of the Cauchy problem. Okay, so the entire Cauchy problem goes in, a single approximation comes out, and that's what I'm going to call my nth order approximation map, and it's local. And then I'm going to define what we call time step methods. A time step method is where we're given a specific time step delta t, this is some number greater than 0, over which I'm going to perform my local approximation. And I'm going to create an iterative scheme, right? It's a time step method. It's going to be an iterative scheme where I start at my initial condition. Maybe I'll write this down. Start at initial condition. And then I update with a sub n. That's my script A. I'm just bad at drawing it. A sub n on the IVP where the initial value is my previous approximation. So my previous approximation, in this case, y sub k. So that's the initial value at time. My initial time plus however many delta t time steps I've managed to take. And so that's what we can see here, right? So y sub k at the specific time of moving forward k time steps from my beginning. Okay, so basically what's happening here is I'm freezing time, I'm re-evaluating an initial condition at wherever my other approximation has put me, and then I'm re-performing this algorithm, which gives me a local approximation. And the way that I get maybe the global approximation is this is a sequence of points, right? So what I've constructed here is actually just a sequence of points at specific times. The time is t0 plus k delta t for the specific y value of y sub k. And then, so I need some sort of interpolating function for us to have actually a global nth order method. The global truncation error gets defined just like with the local truncation errors, except rather than just calculating an error at a specific delta t, I'm now going to give myself a time t max that I'm just calling my maximum time. The global error is just the maximum of the difference of the true solution to the approximate solution over that time interval. Not a very important thing to talk about. I won't talk about this too much in this chapter. I shouldn't say it's not an important thing to talk about. This is important. It's just not for this chapter important. This will be important for other reasons. And we don't really have an idea of orders of global truncations because this sort of big O notation was local by its nature. You're taking a limit in the big O notation, and here you're very clearly not considering a limit, right? We have an entire interval there. But we do have the following proposition, which kind of gives us a little bit of an idea on the way that orders behave for global truncations. So if I give myself a number capital L, which I'm just calling the maximum value of my derivative of my nonlinear operator over the time interval t0 to t max and also over all of space. Okay, so this is just some constant, ideally, that is bounded. In some cases it won't be. But the global truncation error would be at most this quantity, right? This is just an exponential of a number. I'm calling L an actual number here. Exponential of a number times the difference in time minus 1 over L. Take the absolute value of that, and then you're actually order delta t to the n in that quantity. So that's like a very interesting proposition we have that gives us a little bit of an idea of the order, right? So if I have a local approximation, recall, if I'm using a sub n, then locally I have something like y t minus y tilde t is less than or equal to O delta t to the n plus 1. That's in some local sense. I should say it's just equal to O delta t to the n plus 1. So that's a local sense. In global sense, I lose 1 power of delta t plus possibly whatever that constant would be. And so that's the interesting thing about kind of talking about orders. Maybe I'll say heuristically. By the way, that word means intuitionally in many ways. It means the way to think about it. So heuristically, we lose 1 order of approximation when moving local to global. So that's what that proposition is saying heuristically. Okay, you basically are jumping down in an order of approximation because of kind of at each time step you can be spreading just a little bit, and those spreads certainly have to accumulate, right? But the following is actually the step-by-step process that we want to think about when we're talking about global approximations. Okay, so everybody probably pause your screen right now and circle this or pay attention to it, because this is what you want to be thinking about for this section in particular. Step 1, we're going to choose a relevant order, n, a time step, delta t, and a maximum time, which we're calling t max, for which an approximation is desired at, right? So if I say I need an approximation out to 37 seconds, then t max is 37 seconds. Choosing the time step is somewhat arbitrary, and you try to make it as small as possible so that your computer can actually handle it. And then the relevant order just depends on how computationally intense you want your code to be, because the higher order, the more intense your code's going to be. Step 2, we're going to define k max is going to be the difference in time divided by delta t, because we're thinking in our heads this is the total number of iterations that we're going to have to run through to get an approximation starting at t0 and ending at least t max. We also will have to choose an approximation of the order n, which we came up with in step 1. Let's call that script a sub n. Okay, so then step 3 is going to give us, we're going to use script a sub n to gain an nth order approximation to our IVP near t0, and we're going to evaluate that approximation 1 time step. So evaluate approx 1 time step in future. Now recall, time step delta t should be small, so 1 time step in the future should be a very good approximation. What we do then is we use script A on the new IVP, where the new IVP is going to be given here. So since we just evaluated our approximation at delta t time steps in the future, we use the new IVP starting at that time in the future, but with everything else in the IVP the same, and we're going to use a sub n on that IVP. And that's going to give us yet a new approximation, y tilde, at a new time, which is now 2 time steps in the future. And then finally, step 5, we can repeat this step to construct a new IVP at every new time in the future, right? This is going to start at 2 delta t, and then it's going to move to 3 delta t, then it's going to move to 4 delta t, and so on. And at each step, we're going to update our approximation at that specific time. And you're going to continue this all the way until you get to k max delta t's, because that number is necessarily greater than or equal to t max. And we have an approximation starting at t0 because we got it right here. Well, actually at t0 we know what the value is, and then we got an approximation at delta t0 plus delta t, and then all the way up to an approximation at t max, or perhaps a little bit past t max. So let's look at an example of that. We're going to construct a second order global approximation, which would hence be first order. This should be, first order global truncation error. This is a little bit frustrating that you use a global approximation. Order of global approximation does not agree with global truncation error. To the IVP, y prime equals y squared, and y is 0 equals 1. Okay, keep in mind, we already know the solution to this by last chapter. The solution is 1 over 1 minus t, but we're going to see whether or not we can actually approximate that relatively well using some approximation scheme. And we're going to do this with time step 0.1 up to t max 0.8. And so following our steps, we're going to use linearization here because that's the only local approximation we've discovered so far. So we're going to use linearization, but let's actually follow our steps, right? So step 1 says we've actually been told that n has to be 3 because for an nth order, n needs to be 2. We've been told that n needs to be 2. That's a typo. And linearization fits the bill there. We also know that for t max, we were told is 0.8 and delta t is 0.1, so we have that k or k max is 8. Total number of iterates we have to make is 8 here. In step 2, we need to find an algorithm which is actually of second order, and theorem 12.1.11, which is our linearization theorem, provides an example of an A2. Once again, I was thinking it was order 3 for some reason. An A2 algorithm. And using A2 on the IVP, we are going to linearize, right? So if we linearize at the initial condition, we recover that the IVP y prime equals 2y minus 1 and y 0 is 1. And we get an approximate solution, which is 1/2 e to the 2t plus 1/2. Evaluating this approximate solution at t0 plus the time step, which happens to be 0 plus 0.1, right? Because we started at t0, our time step is 0.1. We're going to evaluate the approximation at 0.1. We recover an approximate answer of 1.1107 at 0.1. Moving to step 4, we actually linearize a new IVP, decimal there, a new IVP at 0.1. So we're linearizing now at the time 0.1, and linearizing at that time gives us the following IVP, where now y prime is 2.2214y minus 1.2337. And our initial condition is y at 0.1 is 1.1107. Now the solution to that is the following, in beautiful decimals. We evaluate this solution one time step further, and we get y approximately at 0.2 is 1.24884. Finally, step 5 says repeat step 4 until we recover the sequence, which I've provided in a table for you. What I'm describing here is that after 0 time steps, my exact solution is 1, my approximate solution is 1 because they start at the same place. After 1 iteration at 1 time step, which is 1 delta t into the future, my exact solution is 1.111, but my approximate solution, which this has given me, is 1.1107. And going all the way through and calculating all of these by just iterating on the previous one at a specific time step, we recover that set of points. And if I plot this set of points against the exact solution, we see the following, right? And if I jump all the way back to before we came up with a global method, that's before we had a global method. This is local approximation at 0. We have the red, which is the approximation, to the black, which is the true solution. And if I scroll down, if I run my global algorithm at 0 out to 8 iterations, then I recover the red against the black, and you can see we have such a good approximation here. It starts to diverge, but it really takes a long time to diverge from what the true solution is. And so that's where linearization can get you in global methods, but it's actually really hard to go through linearization at every single iteration, right? Linearization has never really been that fun of a procedure, and at every iteration, that's a whole lot of linearizations that I have to perform. So the question is there a better approach to something like this? And the answer is definitely yes. We're going to start with the Euler method. So the Euler method is probably the best approach to global approximation. The best approach. And I'll just say for now, because you'll wait 1 week and then you'll have a better one, to global approximation. It's the most natural approach for sure to global approximation. So definitely the most natural and possibly the best for maybe early an introduction to global approximation. So let's talk about what it is. If we think about the derivative, it's the limit is delta t goes to 0 of y of t plus delta t minus y of t divided by delta t, right? This is your classic limit quotient of the derivative. And we can approximate the derivative by letting t, delta t, be a very small number, right? If the limit's ending up at 0 plus, then t could be a very small number. And then we have this sort of difference quotient, which is truly a secant line, right? But it's a very good approximation to the derivative. Okay, well, to kind of talk about this in a little bit more concrete detail, I define the following, which is called the finite difference operator. And this is just an operator I call delta sub h, which says, hey, we're going to move forward by h, but we're actually going to subtract where we started. So it's the difference by some time h from where we started. That's the finite difference operator. This is an approximation to the differential, or alternatively, if we divide it by h, it's an approximation to the derivative in time. And so the next proposition is pretty nice, right? It just says as long as h goes to 0, this operator, right? Because up here, this is truly an operator. The operator converges to d dt. So since we have that nice property, we know that this finite difference equation, it's not actually a differential equation anymore, but this finite difference equation actually is a good approximation to the differential equation that we're starting with. And so by solving the finite difference equation, we might gain a solution to the differential equation, or an approximate solution to the differential equation. And this is the Euler method. The Euler method says, given the IVP, which I start with, I'm going to approximate it with a finite difference equation. I'm going to initialize the finite difference equation at the same initial value, but I'm approximating the derivative in the finite difference equation. And then if I solve the finite difference equation, I have an approximate solution to my problem. Now I'm going to scroll down here to this remark, because this is what you'll want to keep in mind when it comes to Euler. This is why the remark is one last interpretation, or also known as the actual Euler method, which I guess I was calling in the previous remark. So there are two remarks there you can read, but I would keep in mind with this actual, this one last interpretation Euler version. And what we want to think is that we're just going to define y tilde sub k as the approximate value of y at the kth time step from t0. Then the Euler method solution is given by the following. We start at y0, and then each iterate is our previous one, plus delta t times the nonlinear term evaluated at the specific time we exist on the previous term. So this is a really, really truncated down version of what we were doing before, where we just start we iterate, and each term gives us the next by saying, okay, we're gonna plug that term in, and we're gonna add delta t times the nonlinear term evaluated at my time and evaluated at my place. In other words, this is kind of like the vector field solution to the differential equation. But let's actually see this in action. Let's use the Euler method with time step 0.1 to approximate the solution to the same problem we were approximating earlier, and the same number of time steps with the same sort of delta t that we did before. We're going to see why the Euler method is a lot easier here. So all we have to do for the Euler method is we initialize at our initial condition, and then we use that initial condition. So I'm using red here to denote the previous term. We use that initial condition plus the time step with the nonlinear term, the nonlinear operator on our previous condition. So let's make that a little clearer here. This initial condition goes there and there, and we get 1 plus 0.1 because that's our time step. N here is just squaring 1 squared, and we end up with 1.1. Okay, then the next step, I use the 1.1 in place of the previous one. And so I have 1.1 plus 0.1, 1.1 squared, and I get 1.221. I use 1.221 to find the next iterate by just plugging it in and adding 0.1 plus 1.221 squared, and I get the next iterate. And I repeat this process until I reach my 8th iterate, right? I started at 0, I end at 8 after 8 time steps, and I end up with 3.2397. Now, what is this line telling me? This is saying that this is approximately y at t0. This next one is approximately y at t0 plus delta t, which in this case was y at 0.1. Approximately y at t0 plus 2 delta t, which in this case was y at 0.2, and so on, and we eventually get approximately y at 0.8. Okay, so I'm pairing these with these numbers, right? I circled the wrong ones there, but you get the idea. And so what we get is a sequence of points which approximates my solution, and we can see here that it approximates the solution relatively well, definitely longer than the 0.2 that I was kind of getting a good approximation with the linearization, the local linearization. This is definitely worse than the global linearization, and that's because the Euler method is actually a first order method. It's not the second order method like our linearization was. But I gained a sequence of points, and it was a lot easier for me to implement the Euler's method up here than it is to relinearize at every single time step. And we'll see how to get Euler-like methods that are better in the future. Now, if you want maybe a better function here than just a collection of points, maybe you want to interpolate these points, there are two interpolation methods that are pretty common to interpolate the points. The first is linear interpolation, where you're literally just constructing a piecewise linear function in between every single one of those points. And you could construct that directly if you want. It's pretty easy to construct a piecewise linear function. But the other case is Lagrange interpolation, which you should remember from the beginning of this entire semester is actually exercise 1.2. I think this is the second exercise you did this entire semester was Lagrange interpolation. You can see you actually get a very nice approximation if you use Lagrange interpolation because everything's smooth. Next proposition says that the Euler method's first order global approximation, which is not as good as the linearization, but it's still pretty good and pretty easy to implement, and I have a proof there for you. And actually that's all I have. So we're going to be moving on to some better methods because we wouldn't necessarily want only first order approximation schemes, but the Euler method is actually really easy to implement. So the idea in the next section is, can we get an Euler-like method that's really easy to implement, but is a much higher order approximation? Because the linearization is hard to implement, but you get a pretty good approximation. Can we get something that's easier to implement that's just as good of an approximation? But anyway, that's all I have. I'll see you in class. Bye.